today's lecture we will be taking up the topic diffusion in plasmas. Diffusion, why do you need to study diffusion? Because it is a very important problem in plasma physics. The references, before I go into the details of the problem, I would like to tell you about the references for this particular lecture. These are Introduction to Plasma Physics by F. Chen and Introduction to Plasma Physics by R. Fitzpatrick. Now, as I said, why do we need to study diffusion phenomena in plasmas? One of the reasons is that plasma confinement is a key problem in plasma physics and engineering. It is very important, particularly in controlled thermonuclear fusion, which is a very active area of research today. You have learned in the initial lectures that realistic plasmas have a density gradient which gives rise to pressure gradient. Now, plasmas tend to diffuse because of the pressure gradient. Therefore, it is important when we need to confine plasmas, it is important that we study the diffusion of charged particles in plasmas. Plasma diffusion can occur at different rates. It is a phenomenon which happens in the presence of magnetic fields and even in the absence. So, with and without magnetic fields, we intend to study the diffusion process in plasmas. You also know that plasmas are collisional as well as collisionless. Collisional plasmas can be categorized into two types, fully ionized and weakly ionized. What is the difference between the two types of plasmas as far as today's lecture is concerned? We will be taking up weakly ionized plasmas in which we will consider the collisions of charged particles with neutral atoms. So, we are discussing diffusion in collisional weakly ionized plasmas to begin with in this lecture. What is a weakly ionized plasma? As I have said, in a weakly ionized plasma, collisions occur between charged particles and neutral atoms, and so we study the effect of collisions between plasma particles for their diffusion, and diffusion, as I said, occurs mainly because of collisions between charged particles and neutral atoms. In this lecture, we will study the effect of collisions first, define the collision parameters, define the diffusion parameters, and solve the equation of motion in the absence of magnetic fields. We will also obtain the diffusion coefficient for ambipolar diffusion and for a very special case of diffusion in laser produced plasmas. Why are weakly ionized plasmas important? There are many examples of weakly ionized plasmas around us. I have taken up the example of an aurora. In an auroral emission, this kind of aurora, the one that I have taken up, I am showing you the picture. Electrons collide with oxygen atoms to produce light of wavelength 557.7 nanometer. This is a weakly ionized plasma. Other examples of weakly ionized plasmas are plasmas in the laboratory, ionospheric plasmas, high pressure arcs. The study of weakly ionized plasmas and diffusion phenomenon in this kind of a plasma is also important because of the industrial applications of such plasmas. I have chosen two such applications. One is that of plasma nitriding. When metallic surfaces are placed in a weakly ionized nitrogen plasma, what happens is that nitrogen atoms diffuse into the surface of the metal, and this causes surface hardening. This kind of a treatment in a weakly ionized nitrogen plasma prevents the wear and tear and corrosion of the metal. And so we find that the gears of cars, knives and other industrial components are treated with such weakly ionized gaseous plasmas. Similarly, there is another interesting application, that of plasma treatment of textiles. Now, textiles are moved in weakly ionized plasmas to change their surface chemistry and chemical composition and to attain desired properties in the material, in the textile. For example, plasma treatment of wool makes it shrink resistant. Cotton is treated by this kind of a plasma and it makes it hydrophobic, which means that water does not stick to cotton, and synthetic textiles are treated in this kind of a plasma to make them hydrophilic. So, water absorption by such plasma treated synthetic textiles increases and they become comfortable to wear in summers. So, amongst many other applications of weakly ionized plasmas, these are two very interesting industrial applications where diffusion phenomenon is primarily responsible for these properties. So, that is why we study weakly ionized plasmas. As I have said earlier, what is a weakly ionized plasma? It is a non-uniform distribution of electrons and ions in the background of a large number of neutral atoms. In this figure, I have shown the model of a weakly ionized plasma. If the color is distinct to you, then the red colored smaller dots are the charged particles. Now, as the plasma spreads out due to pressure gradient and electric field, individual particles undergo a random walk, colliding frequently with neutral atoms. So, we are essentially treating the diffusion in weakly ionized plasmas as a random walk problem of charged particles amongst a dense background of neutral atoms. This is the model. So, diffusion in weakly ionized plasmas is shown here in this figure. This takes place due to random collisions of the particles with the atoms. So, you must remember that in a weakly ionized plasma, charged particles collide primarily with neutral atoms and individual particles collide in the manner of a random walk. They collide frequently with neutral atoms and we treat it as a random walk problem. So, we can apply the results that we already know from our college physics for the random walk problem. This is the kind of animation which shows the random walk for a weakly ionized plasma or diffusion due to random collisions. It is available on the common Wikipedia Commons. I have given the source here. Now, when we treat the collision as a random walk problem, the collision parameters that we need to know are mean free path, collision frequency and collision cross section. So, let us go back to the college physics and see how we can obtain the definitions and the expressions which are relevant to plasma physics. You may recall that the mean free path is the mean distance travelled by a particle between two successive collisions. So, if lambda 1, lambda 2, lambda 3, lambda 4, lambda n are successive free paths which the particle travels in time t in n collisions, then we have lambda m is equal to sigma I lambda I upon n. This is the equation that defines the mean free path. It is a simple algebraic equation. This is a pictorial representation of the mean free path where the electron or the charged particle is colliding with different atoms in the plasma and in a random manner. Now, if v is the average speed of the particle, then lambda m, which is the sum of all the free paths, can be written as v multiplied by the total time t divided by n, the number of collisions. Let us say that tau is the mean time between successive collisions. Then if the total time is t and n is the number of collisions, the mean time between successive collisions is nothing but tau equal to t by n. So, combining the equation lambda m equal to Vt by n and tau equal to t by m, we get an expression lambda m equal to V tau, from where tau is equal to lambda m upon V. This is the mean time between collisions, and from here we get the expression for the collision frequency, which is 1 upon the mean time tau and is given by V upon lambda m. The collision frequency is nothing but the average number of collisions per second. So, these parameters you must be familiar from your usual college physics in the kinetic theory of gases. We are going to apply this now to plasma physics. I have summarized the results in this slide for you, where I have given the mean free path, the mean time between successive collisions and the collision frequency. The mean free path is lambda m equal to Vt upon n. Mean time between successive collisions is tau equal to lambda m upon V, and collision frequency is simply 1 upon tau equal to V upon lambda m. So, these are the collision parameters which are for any random walk problem. These are the definitions. But we still need to know what the collision cross section is, and we still need to ask how is lambda m related to the microscopic properties of the plasma, because we need to apply these concepts to plasma physics. So, what are the properties of the plasma? The number density and the collision cross section are some of the properties, two of the properties to which we can relate the mean free path. So, we first define the collision cross section and then find the relation between lambda m and the plasma properties, the collision cross section and number density. Now, in the collision theory, each collision is described by a collision cross section sigma. What is this? What is the definition of the collision cross section? Let us just look at an example of a very famous scattering experiment. This is the animation. We will be discussing this sometime later, the Rutherford scattering. It is a very famous experiment in physics where alpha particles were bombarded on very thin gold foils, and whereas the existing Thomson's model predicted that all alpha particles would just pass through the gold foil, what was observed was that some of them just bounced back. There was a back scattering. We will not go into the details, but this is the kind of an experiment in which you can determine the collision cross sections. So, what is a collision cross section? There are two kinds of cross sections. One is called the differential cross section and the other is called total cross section. We define the differential cross section as number of particles scattered per unit time in a solid angle in a given direction divided by incident flux. What is the incident flux? It is the number of particles incident on the target per unit area per unit time. So, let me just show you the experimental setup. First, This is the experimental setup where the incident beam is bombarded on the target and then it is observed in a solid angle. You see a solid angle which is centered at the scattering angle theta. It is the cone. You can imagine it to be a cone centered at the at the scattering angle theta and between theta and theta plus d theta. So, if you count the number of particles scattered in this particular solid angle detected by the detector here, then the number of particles scattered per unit time in a solid angle in the direction theta divided by the number of particles incident on the target per unit area per unit time is defined as the differential cross section. Now, the interesting thing is that the dimension of the differential cross section is that of area. So, if you want to understand what it is physically, we can say that it is the effective area offered by this target or the scatterer to the incident beam of particles. It is the effective area offered by the target to the incident beam of particles. This is an important concept we will be using later in this lecture. So, this is once again the schematics of a scattering process. You are counting the numbers of particles in this solid angle and then you divide it by incident flux. So, there is another parameter called the total cross section, which is you count the total number of particles scattered. You place the detector at all angles, all possible scattering angles around the target and you count the total number of particles scattered by the target, you get the total cross section. Mathematically, you just integrate the differential cross section over all values of the solid angle. Physically, it means the total area offered by the target to the incident particles. These two things, the physical concept is more important for you to remember as far as the further treatment of this process of diffusion is concerned, that it is the area offered by the target atoms to the incident or the colliding charged particles. Now, an interesting point as far as plasmas are concerned is that collisions are of two types, elastic collisions and inelastic collisions. Elastic collisions are those in which the momentum and kinetic energy of the system of incident particles and target particles are conserved. So, the total linear momentum and the total kinetic energy are conserved in this process. Inelastic collisions are the ones in which the linear momentum or momentum, it could be angular momentum also, as we will see in the scattering of charged particles by atoms in a plasma. Momentum is conserved, but kinetic energy is not conserved. And so, there can be energy loss due to heat loss in plasmas. Inelastic collisions taking place in plasmas give rise to energy loss by way of heat loss. Now, having defined the collision cross section as an effective area or the total area offered by the target atoms to the colliding electrons or ions in a plasma, let us find out what its value is for a weakly ionized plasma. As you have learnt earlier on in this lecture, in weakly ionized plasmas, charged particles collide mostly with neutral atoms and molecules. So, let us say that they are colliding with neutral atoms and let R be the effective radius of the neutral particle. We can describe this scattering process using the hard sphere scattering model, and in the hard sphere scattering model we assume that the charged particles, the incident charged particles, say the radius is RE, and the neutral particles of radius R are hard spheres. What does this mean? This means that the spheres cannot penetrate each other. So, they cannot penetrate a distance that is smaller than Re plus R. If this is one sphere of Re and another sphere of R, they cannot get into each other. This will be the distance, smallest distance between them, Re plus R. Without going into the derivations, I am just giving you the result of the collision cross section for hard sphere scattering, which is shown here, and it is shown, I have also written it down for you. It is sigma equal to pi Re plus R whole square. Now, since Re is much less than R, the radius of the charged particle, which is either an electron or an ion, is much less than the radius of the atom or the molecule, we can say that sigma is equal to pi R square. So, pi R square is the effective cross section of the target atom or molecule. So, assuming the hard sphere scattering model, we have arrived at an expression for the scattering cross section that sigma is pi R square. This is the effective area offered by the target atom or molecule to the charged particles in the plasma. Now, how do we express the mean free path in terms of this collision cross section and number density? Imagine a cylinder in the plasma, and there are certain atoms or molecules, and a charged particle collides with those atoms and molecules in that particular cylinder. Let the cross sectional area of the cylinder be pi R square, which is the area offered by an atom or a molecule to the incident charged particle. So, if we take a cross sectional area pi R square, in time t, let us say it sweeps out the cylinder shown here on the slide. Then what is the mean free path as per our original definition? It is the mean distance per collision. So, it is equal to the length of the path divided by the number of collisions. This is what we had done in our basic definition, sigma lambda I upon n. What is the length of the path traversed by a charged particle? It is the speed multiplied by the time in which we have taken the cylinder, divided by the number of collisions is just volume of the cylinder multiplied by number of target atoms per unit volume. So, this is what it is. Mean free path is distance travelled divided by volume into number density. Distance travelled is simply Vt. You can see it in the expression of lambda m. Vt and volume is pi R square multiplied by the length Vt, and number density is Nn. We have denoted it by Nn, number of atoms per unit volume in the plasma. So, Vt and Vt cross out and we get lambda m as 1 upon pi R square Nn or 1 upon sigma Nn. So, this is nothing but the mean distance per collision. We have obtained an expression for the mean free path in terms of sigma, the collision cross section, and the number density. From there, it is simple to get the mean time between collisions, which is tau, and lambda m upon v. This is what is given here. Tau is equal to lambda m upon V is equal to 1 upon sigma nn V, and collision frequency is simply 1 upon tau is equal to nn sigma V. Remember, V is the average velocity. So, strictly speaking, we should average both sigma and V over the distribution function for V. So, if we assume Maxwellian distribution of velocities, we can write nu is equal to nn sigma V bar, where V bar and sigma are obtained from Maxwellian distribution. The temperature dependence of the collision frequency then goes as square root T, because sigma is a constant and V bar goes as square root T. To summarize the collision parameters, we have established 4 of them: the collision cross section, the mean free path for collisions in terms of sigma and nn, mean time between collisions, and the collision frequency. We shall be using these parameters. The next category of parameters, before we go to the next category, the diffusion parameters, it's an interesting thing to understand physically what this mean free path is as far as plasmas are concerned. To do that, we need to relate the mean free path to the flux of the particles. So, as shown in the diagram here, let us consider a slab of area A and thickness dx in the plasma, and these are the incident charged particles incident on the slab. They could be electrons, they could be ions. You know that the number density is nn atoms per unit volume. So, the number of atoms in this slab is nn multiplied by the volume of the slab, which is A dx. If the cross sectional area of these atoms is sigma, then the area that the slab offers the incoming particles for scattering is sigma multiplied by the number of atoms in the slab, which is sigma nn A dx. AS, we are denoting it by AS, this is sigma nn A dx. This is the pictorial representation of this process, area offered by the slab in the plasma to incoming charged particles. Now, this is a fraction of the total area. So, the fraction of the slab area that blocks the incoming charged particles is simply AS upon A, which is sigma nn dx, because A cancels out. So, this is the fraction. Now, we come to the incident flux. What is the expression for the incident flux? If F is the incident flux and F is incident on the slab, then some part of the incident beam is blocked, which is sigma nn dx. So, that much flux will then be blocked by the slab. Sigma nn dx is the fraction multiplied by the incident flux. That much flux will not emerge from the other side of the block. So, the flux of particles emerging on the other side of blocks is simply F minus F sigma nn dx. Now, this gives me an expression for the change in flux. This is df, this is the change in flux, is equal to F prime minus F is equal to minus sigma nn F dx. So, the change in flux with distance comes out to be a first order differential equation. Df upon dx is equal to minus sigma nn F, and its solution is an exponential solution, exponentially decaying solution. You have come across these kinds of equations elsewhere at many places in physics. I will tell you in a moment. Now, for this kind of an linear exponentially decaying function, you can see that when x is equal to 1 upon sigma and n, then f is equal to f0 upon e. F is reduced to 1 by E of its initial value. So, this is the length in which the flux is reduced to 1 by E of its initial value, and you will recall we have just obtained an expression for lambda m as 1 upon sigma n n. So, f becomes f0 exponential minus x upon lambda m here. So, what does this equation tell us? It tells us that in a distance lambda m, the flux would be decreased to 1 upon E of its initial value. After travelling a distance lambda m, a particle will have a finite probability of making a collision. Such equations you have come across in radioactive decay, as well as these are also equations that you come across in radiation biology, where it gives you the depths to which radiation, electromagnetic radiation, can penetrate biological systems. But that is a different story. Now, having understood the collision parameters, we come to the diffusion parameters and we define the diffusion coefficient and mobility. For introducing the diffusion parameters in collisional plasmas, we have to account for the momentum removed due to collisions. So, we have to modify the fluid equation of motion, and the momentum that is removed by collisions is given by this equation: dp upon dt is equal to minus p upon tau is equal to minus mn nu v. Nu comes from 1 upon tau. When we write this particular term in the equation of motion, the collision term, the equation of motion becomes this: mn dv by dt is equal to mn del v by del t plus v dot del v, the convective term. And in the presence of electric and magnetic fields and the pressure gradient, we have to add the collisional term. We solve this equation of motion under certain simplifying assumptions, and those are that firstly we consider the case of unmagnetized plasma. We will take up magnetized plasmas later and take the V cross B term also, but not today. So, for unmagnetized plasma, B is equal to 0. Further, we take only the steady state solution of the equation of motion. So, we put del V upon del T also 0, and we make another assumption. Physics is all about simplifying the problems. So, we make another assumption that the drift speed or drift velocity is very small, so that the second order term or the convective term can be neglected in the equation of motion, the V dot grad V term. So, we are left with these three terms: q n E minus grad P minus m n nu V is equal to 0. This is the equation of motion that we need to solve. So, here again I have written the assumptions and the equation of motion. Now, from this equation of motion, we can immediately write an expression for V, which is q n E minus grad P upon m n nu, and we get two terms. We can express them in terms of two terms, and for the case of isothermal plasmas, the pressure gradient term can be expressed as V is equal to kBT grad n, and so we have V is equal to q upon m nu E minus kBT upon m nu grad n upon n. This is the equation solution for drift velocity. In this equation, the coefficient of the electric field q, the modulus of q, we do not include the sign of the charge, q upon m nu is defined as mobility, and kBT upon m nu is defined as diffusion coefficient. So far we have written it only for one kind of charged particles. This is just so that you recognize the expressions. interesting point about the diffusion coefficient is that it has the dimension of L square upon T. You can readily show this yourself by writing the dimensions of all the quantities. You will find that it comes out to be lambda square upon tau, which has the dimension length square upon T. Now, we express the flux in terms of mobility and diffusion coefficient. Flux is Nv is equal to N. You substitute for V, you get an expression straight away, which can be written as plus minus mu Ne minus d grad N. This is a simple expression. The sign plus minus comes due to the sign of the charge Q. So, we get an expression for the flux in terms of the electric field and the density gradient. And when we put the electric field equal to 0, what do we get? We get that the flux is proportional to density gradient. F is equal to minus d grad N. This result is known as Fick's law. And what does Fick's law tell us? It tells us that diffusion is a random walk process, and this arises because a net flux from dense regions to less dense region happens because more particles start in the dense region. The flux is proportional to density gradient. However, you do know that electric field is not exactly 0 in a plasma, because electrons have higher thermal speeds than ions. The diffusion coefficient at the same temperature, the diffusion coefficient for electrons is greater than the diffusion coefficient for ions, and so electrons diffuse faster in the plasma. This leads to an imbalance between electron and ion densities, creating an electric field. However, what happens is that the electric field so created acts in a direction that slows down the electrons and speeds up the ions. So, until the time that both of them diffuse at the same rate. This phenomenon is called ambipolar diffusion, in which the electrons and ions diffuse at the same rate, both. Ambi means both, and so both kinds of charged particles diffuse at the same rate. Now, we will solve the equation of motion for ambipolar diffusion to obtain an expression for the diffusion coefficient. Let us go back to the equation of motion for isothermal plasma, which was Q n E minus kBT grad N minus Mn nu V is equal to 0. We can write it for electrons and for ions. For electrons, this becomes minus EE. We divide the equation by N. So, we get minus EE minus kBTE upon Ne grad Ne minus Me nu E Ve is equal to 0. Similarly, we write this expression for ions. The charge is plus E. So, we get EE minus kBTI upon Ni grad Ni minus Mi nu I Vi is equal to 0. So, what have we done? We have simply written the equation of motion for isothermal plasma for both electrons and ions. We have divided the equation by the number density, and we have used the charge minus E for electrons, and then temperature for electrons is Te, number density is Ne, and collision frequency is nu E, and mass is Me. Similarly, for ions, the charge is plus E. So, we have EE The temperature is Ti, the number density is Ni, the mass is Mi, the collision frequency is nu I, and the velocity is Vi. We have written the equation of motion for electrons and for ions. Now we would like to obtain an expression for the diffusion coefficient for ambipolar diffusion. How do we do that? What we do is simply add the equations, add the two equations that I have shown you for electrons and for ions. So, what do we get? We get an expression E minus kBTi upon Ni grad Ni minus Mi nu I Vi minus E minus kBTe upon Ne grad Ne minus Me nu E Ve is equal to 0. The term E and minus E cancel out. E and minus E cancel out, and we are left with minus kBTi upon Ni grad Ni minus Mi nu I multiplied by Vi minus kBTe upon Ne grad Ne minus Me nu E Ve is equal to 0. It still looks a pretty complicated equation, and so we solve it under certain assumptions which are valid for the case that we are considering, which are, because the ions and electrons are diffusing at the same rate, we can say that Vi is approximately equal to Ve. I have written it down for you. Vi is approximately equal to Ve. The number density we can assume to be approximately equal, and we put it equal to n, but the product, since ion mass is much greater than Me, the electron mass, the product Mi nu I is much greater than Me nu E. So, we neglect the term Me nu E Ve in this equation, and we put Ni equal to Ne equal to n, and we put Vi equal to Ve equal to V. So, we are left with this equation minus Mi nu I V minus Kb upon n multiplied by Te plus Ti within brackets grad n is equal to 0. This is a much simpler equation compared to the earlier one, and from here we can immediately write a solution for the velocity. I have repeated the equation in this slide for ready reference. The expression for velocity then becomes V is equal to minus Kb Te plus Ti upon Mi nu I n grad n. So, you can readily see that the diffusion coefficient for ambipolar diffusion is simply D is equal to Kb Te plus Ti upon Mi nu I. This is a simple enough expression for the diffusion coefficient for ambipolar diffusion. Now, using the information using whatever we have learned so far, we can write down the continuity equation or the diffusion equation and try and solve it for some special cases. As you know, the continuity equation is, you are familiar with it, is del n upon del t plus del dot f is equal to 0. This is a scalar equation because the divergence of f is a scalar. Now, a little while ago I have shown you that for a plasma, weakly ionized plasma, in the special case when E is equal to 0, the electric field is 0, which happens to be the case for ambipolar diffusion also. The flux is simply negative of diffusion coefficient multiplied by the density gradient. This is the Fick's law. And so, if we substitute this expression of the flux from Fick's law, what do we get? We get del n upon del t minus d del square n is equal to 0. Again, this is a 3-dimensional equation and it can be solved for special cases. And one of the interesting special cases, there are many cases that have been taken up in the reference books that I have cited, F. Chen as well as Fitzpatrick and any other textbook on plasma physics that you will be studying in this course. But we have, for this particular lecture, I have chosen a special case of laser produced plasmas. So, for a very special case of laser produced plasma, we will solve the equation and obtain an expression for the diffusion coefficient. What happens in this process? You have a thin foil which is shown on the screen and you bombard that with laser beams. What happens is that a plasma plume is produced. This is the plasma plume that is produced when laser beams bombard a thin foil. What are we interested in now is how the plasma particles will diffuse in this plasma plume. What will be the diffusion time? This is a case of a weakly ionized plasma. This is a kind of a Gaussian density distribution and we can solve the equation by assuming a distribution for the number density which goes as n is equal to n0 e raised power minus x square by a square. This is a reasonably good approximation for the plasma plume that is formed when laser beams are bombarded on a thin foil. So, if we assume this, we have assumed a one-dimensional function for the number density. It is e raised power minus x square upon a square. So, this then turns into a one-dimensional differential equation in time and length, say x. So, del square n is simply d square n upon dx square. I have not written it here. Del n by del t, I can write this equation maybe here on the graph paper. Del n, this is the original equation, del n upon del t minus d del square n is equal to 0. We have assumed a one-dimensional expression for the number density. So, essentially we get what? Let us say dn by dt minus d square x d square n by dx square is equal to 0. This is n. So, all we need to do is find out d square n upon dx square. I hope it is clear to you that this is n. We find out the value of d square n upon dx square, and let us see what happens. So, what we need to do is differentiate this expression with respect to x twice, and this is what we get. These are 3 terms shown here. When you differentiate it once, you get these 2 terms, and differentiated once, you get minus 2x e raised power minus x square by a square upon a square. This is first derivative. Differentiate it again, you get these 2 terms, right. So, when you simplify, you can write it as this: n0 e raised power minus x square upon a square is nothing but n here. N is n0 e raised power minus x square upon a square. So, you just take this common factor out and put n0 e raised power minus x square upon a square equal to n, and within brackets you are left with minus 2 upon a square plus 4x square upon a 4. So, this should have been x square. So, I am sorry, this should have been x square. Shall I write this equation again for you, so that for the sake of correctness? Del n upon del t is equal to d n0 minus, because it is the second derivative of this particular expression, or the derivative of this. So, you differentiate x, you get this, and you differentiate here, you get x square. So, this becomes minus 2 upon a square e raised power minus x square upon a square plus, it should be 4x square e raised power minus x square upon a square, and the whole thing divided by a4. So, this should be the expression, and so we take e raised power minus x square upon a square out of the bracket, multiplied by n0, we get n, and within the bracket we get minus 2 upon a square plus a second order term in x upon a4. This is what is the correct expression. Now, if we neglect the second order term 4x square upon a4 and retain only the first term, the constant term, we can write the derivative dn upon dt as dn minus 2 upon a square, and you can easily solve this equation to get an expression of n is equal to n0 exponential minus t upon tau d. Tau d is nothing but the diffusion time, is equal to a square upon 2d. Tau d is a square upon 2d, and we get that as a square upon 2 m nu upon kBt, or nu a square upon 2 V thermal square, which goes as 1 upon square root T. The diffusion time in laser produced plasmas is 1 upon square root T. So, it is less when the plasma frequency is high diffusion time, and therefore, we say that hotter plasmas diffuse rapidly. So, this is where we come to an end of this discussion. Let me quickly summarize this for you. What we have done today, in our discussion on diffusion in weakly ionized plasmas, we have defined collision parameters like collision cross section, mean free path, collision frequency and mean time between collisions. We have then defined diffusion parameters, mobility and diffusion coefficient and established Fick's law. We have solved the steady state equation of motion for unmagnetized plasmas and obtained the diffusion coefficient for ambipolar diffusion. Lastly, we have solved the diffusion equation to obtain diffusion time for laser produced plasmas. So, this is an important process of diffusion in weakly ionized plasmas that we have studied today for ambipolar diffusion and laser produced plasmas.